Hi, in this one we make a perhaps surprising connection between a branching process and random walks. I want to start this video with recalling a calculation we did with a special type of branching process or Galton-Watson process. So we had the offspring distribution as 2 with probability p or 0 with probability 1 minus p. So either there was a branching or there was a death event for the individual amoeba, and we found the generating function of the total number of individuals that ever existed in this branching process, and we found this generating function to be 1 minus square root of 1 minus 4s squared pq over 2sp. Okay, and then in a previous video, the previous video, we looked at the return time to 0. Well, we looked at actually first the hitting time of level -1 for simple random walk, and we found this generating function to be 1 minus square root of 1 minus 4s squared pq over 2sp. And if I put these two generating functions next to each other, then you notice something interesting. These two generating functions are the same, which implies that the two distributions are the same. So the total number of individuals in this amoeba process and the hitting time of -1 for simple random walk is actually the same quantity. It has the same distribution at least. What I want to show now is why are they the same quantity. And let me draw you a little example realization. So I have one individual to start with, and for some reason I'm going to draw everything from left to right in time. So I'm going to draw these amoebas, and let's assume that you have, okay, it's not so easy to draw this from left to right, but I'll try. Okay, so at every time either the process either that line dies out or branches into two. So remember that we had either this or that. Okay, and we had branching with probability p and dying out with probability q. Okay, and okay, let's draw one more. So suppose that this is the process, and what I'm going to do now is I'm going to ask every amoeba, and I'm going to record what I see. I'm going to ask every amoeba whether they want to branch or not, and I'm going to number them. I'm going to enumerate them. So this is going to be 1, 2, 3. Notice I'm doing this in a kind of a breadth first manner. So I'm looking at a particular level, and I'm going to enumerate the amoebas like that. So from bottom to up at a given depth, and so this is 11, I believe, and this is 12, and this is 13, and then 14 and 15 and 16 and 17. So I have a total of 17 individuals if I did the enumeration fine. And let's record the number of individuals who ever existed as a sequence in time. Well, okay, so I'm going to be precise in a second. Ten, 11, 12, 13, and I always draw too short of a coordinate axis. Okay, so to be precise, here is what I'm going to start with. This is level 1, and at time 0, I'm going to say that before I ask the first amoeba, I had one individual. At time 0, this is what I'm going to call time 0, at least for the random walk. Notice that this time is going to be different than the time of the Galton-Watson process. So this is what I'm going to call time 0 for the random walk. I have one amoeba at that time. Okay, now I'm going to ask amoeba 1, what do you want to do? Do you want to die or do you want to have two offsprings? And amoeba 1 tells me that they want to do two offsprings. Okay, and that raises the number from 0 to 2. So after I asked amoeba 1, at this moment, I'm going to call this time of the random walk 1. Instead of going to 0 from 1, it's going up to 2. So at this time, I have 2. So my random walk went up. Okay, so this is going to be a random walk. You'll see in a second why. And once I'm done with that, then I'm going to ask amoeba 2. Dear amoeba 2, what do you want to do? And amoeba 2 tells me that she also wants to proliferate. And so after I asked amoeba 2, I'm going to have one more again. So I'm going to go up to level 3 after asking amoeba 2, because now in this line I have 3 amoebas. Okay. Then I'm going to ask now amoeba 3, dear amoeba 3, what do you want to do? And amoeba 3 tells me that rather than dying, amoeba 3 will have again 2 offsprings, which makes this line into 2. So again it's one more. So at this moment I have 4 amoebas in the system. That was amoeba 3. And then I'm going to ask amoeba 5, dear amoeba 5, what do you want to do? And amoeba 4. Dear amoeba 4, what do you want to do? And amoeba 4 tells me that I want to die. Amoeba 4 tells me that I don't want any offsprings. So I'm going to just stop here. And that makes one less of a line. So now this kind of time 4 for the random walk is going to be intersected by 1, 2, 3 only. So that decreases the number back to 3 again at time 4. And then I'm going to ask number 5, dear amoeba 5, what do you want to do? And amoeba 5 wants to have 2 offsprings, so that increases again the number by 1. And then amoeba 6 again wants to increase the number. So now I was back to 4. So now I'm going to be at 5 in here. Okay, because amoeba 6 also decided to have 2 offsprings. So now I'm here. And I guess you can guess how this story proceeds. It's getting more and more difficult to draw. When I ask amoeba 7 decreases the total population by 1 because it dies without an offspring. So that's amoeba 7. Okay. If I ask 8 and 9, they will all again decrease the population by 1. So now I'm back at level 3. After amoeba 8, I'm back at level 3. After amoeba 9, I'm back at level 2. Right? Because after I asked everybody, including 9, I actually only have 2 lines left, namely 10. I didn't ask 10 yet, and I haven't asked 11 yet. When I ask 10, then it goes down to 1. So it almost dies out at this point. Okay, when I ask 10, it goes down to 1. It almost dies out, because at this point I'm only having 1 line left, namely the line that goes up to 11. So when at time 10 for my random walk, I'm down there, but then 11 again decides to have 2 children, and that increases the line, that increases the number of living individuals to 2, these 2. So I'm back to level 2 now. And then when I ask 12, that again goes down to 1, because 12 doesn't have any offsprings. So this is 1 again. And when I asked 13, so this was 12. When I asked 13 will have 2 offsprings, so that increases the number of lines by 1. Then I asked 14, that again goes up by 1. So now I'm up to 3. Okay. And then I ask 15 and 16 and 17, and they all die without offsprings. So I'm going to have 3 steps down, from 3 to 2, from 2 to 1, and finally at this point everybody is dead, and the whole process finishes after asking amoeba 17. Okay? Now what you see here is the trajectory of a simple random walk. Every time going up means that we have a two offspring event, and this happens with probability p, and every time going down means that we have a die out event that's going down in the number. That happens with probability q. Okay, and these are independent for the amoebas because the amoebas do this independently. And what we see here is that we have an up and down process. We have an independent up and down process, which is exactly a simple random walk. So what we see here is exactly a simple random walk. Okay, now there are two cases in this Galton-Watson process. The first case is that there is always going to be somebody. There is infinitely many individuals. It never dies out. In which case I can keep going and never run out of amoebas to us, so I never come back to the origin with this random walk. So the random walk will never hit level 0. Okay? Remember we called the total number of individuals x. Okay? X was the total number of individuals who ever existed. And so x equals to infinity is the same event that the random walk never coming back to the origin. Now, what is the quantity we're looking at? We start from level 1 and we want to hit level 0. So that's exactly the thing we called tau minus. So the event that we have infinitely many individuals is the same event that the random walk never comes back to the origin. The number of individuals never goes down to 0. Asking any number of amoebas, it's never going to run out. Whereas in this picture, it is running out. We asked 17 amoebas in total, and after asking all of them, we found that nobody had an offspring anymore, and so the total number of individuals, well, the number of individuals after asking individual amoebas went down to 0. And it went down to 0 at time, random walk time 17, exactly because we asked 17 amoebas before all of them died out. Okay? And therefore what we find is that when they are finite, then x, the total number of amoebas that existed, is exactly the same thing as the total number of questions we had to ask, and these are the questions from 1 through 17, so the total time we needed to take for the process of simple random walk to go down to 0, level 0, from level 1, right? This is level 0 here. The time it took to go down from level 1 to level 0 is exactly the number of questions we had to ask here, and it's exactly the total number of individuals that ever existed. So there is a probabilistic level correspondence, or if you want a configuration space level correspondence between the two quantities, and so it's not surprising that distribution of the two quantities is therefore the same, and it's not surprising then therefore the moment generating function the generating function is the same. Okay? If the generating function is the same, then of course the probability that the quantity is finite is the same, and the expectation of the quantity is the same. And if you remember what we did with the amoeba process, we actually looked at the probability that the total number of individuals is finite, and we did the same calculation as what we did for the hitting time of level 1, except P and Q was swapped there. It's the same calculation. And the way we figured out the expected tau plus, from there, of course, we can figure out the expected tau minus. Actually, let's quickly do that. So the expected tau plus was calculated on this sheet for symmetric random walk. It turns out to be infinite, of course, if we have a drift to the negative direction, or we have no drift at all. And if we have a drift to the positive direction, it turned out to be 1 over P minus Q. For tau minus, we can do the same. It's actually just a shift, just a swap of P and Q as before. So this is going to be infinite if P is bigger than 1/2, because that's when we have a drift to the right, and it's going to be 1 over Q minus P if P is smaller than 1/2. And in fact, when P is equal to 1/2, it's still infinite. So all I was doing is just copy this line, except swapping P and Q. So if P is smaller than 1/2, that's when Q is smaller than or equal to 1/2 in the new setup, and that's where P is larger than or equal to 1/2, that's when we have infinite. And if P is larger than 1/2, when in the new setup that means P is smaller than 1/2, then it used to be 1 over P minus Q, now it's P and Q swapped 1 over Q minus P. So that's the expectation of tau minus, and because these two are the same, this is of course going to be the expectation of the total number of individuals as well. It's the same calculation, same generating function, everything is the same. It's actually the same process. If you look at these two pictures, it's the same process.